This is an audio recording for visual impaired students. Inorganic Chemistry, Chapter 1, Metal Ligand Bonding in Transition Metal Complexes. Transition metals have very good tendency to form coordination compounds or complexes. Though many attempts were made by different workers to explain the bonding and structure of coordination compounds, the main credit goes to brilliant work of Werner in 1893. Werner proposed a theory, which is commonly known as Werner's coordination theory. This was the first successful attempt to explain the bonding in coordination complexes. In recognition of his work in this field, Werner was awarded Nobel Prize in 1913. He explained the bonding in these complexes on the basis of two types of valencies of the metal, the primary valency corresponding to oxidation state and the secondary valency corresponding to coordination number. The secondary valency or coordination number determined the stereochemistry of the complexes. However, the Werner's assumptions were not based on theoretical justification, and the scientists started making attempts to find bases of bonding in these complexes. The first attempt in this regard was made by Sidgwick, who extended the Lewis theory of electron pair bond formation to explain the bonding in transition metal complexes. He suggested that metal ion or atom accepts electron pairs from ligands until it achieves the next noble gas configuration and gave a term effective atomic number EAN. EAN is the total number of electrons possessed by the central metal ion and the electrons gained by it form ligands. However, this theory lacked fundamental basis and simply gave emphasis on the stability of inert gas configuration in coordination compounds. With the advances in theories of chemical bonding, three modern theories of bonding in transition metal complexes have been developed. These are first, valence bond theory, second, crystal field theory, and third, molecular orbital theory. In the present text, we shall discuss mainly crystal field theory of bonding. The valence bond theory has already been discussed in the previous classes. Valence bond theory. The valence bond theory was developed by Linus Pauling and assumes the bonding between the metal atom or ion and the ligands to be purely covalent. It presents a simple description of metal ligand bonding using hybrid orbitals of the metal and the electron pairs of the ligands. The basis of valence bond theory is that the appropriate vacant atomic orbital of the metal atom hybridized to give a set of hybrid orbital which are directed towards the ligands according to definite geometry of the complex. The bonding in metal complexes arise when a filled orbital of the ligand containing a pair of electrons overlaps with a vacant hybrid orbital on the metal atom or ion, forming a covalent sigma bond called coordinate bond. In addition to a sigma bond, there is also a possibility of pi bond provided suitable orbitals are available on the metal atom and the ligands. The total number of metal atomic orbitals which undergo hybridization is equal to the coordination number of the central metal atom or ion. For example, the coordination number 6 complexes to D1s and 3p orbitals, that is, a total 6 orbitals of the metal atom are involved in hybridization. The d orbitals involved in the hybridization may be either inner n-1d orbitals or outer nd orbitals, giving inner orbitals or outer orbital complexes. For example, in case of octahedral hybridization, the orbitals may be 1ns, 3np and 2nd, or 1ns, 3np and 2n-1d. Similarly, the coordination number 4 complexes tetrahedral structure can be considered to arise from bonding with 4 sp3 hybrid orbitals formed by the combination of 1ns and 3np atomic orbitals, or square planar structure arising from bonding with 4 dsp2 hybrid orbitals using n-1d, ns and 2np atomic orbitals. Some common types of hybridization of atomic orbitals and their geometries are given in table 1. Limitations of valence bond theory. The valence bond theory successfully explained many stereochemical and magnetic properties of coordination compounds. However, it has many limitations. The main limitations of valence bond theory are: first, it provides only qualitative explanation for complexes. Second, it does not explain the color and electronic spectra of complexes. Third, the theory fails to explain why some metal complexes in a particular oxidation state are low spin complexes while some other complexes of the same metal ion in the same oxidation state are high spin complexes. For example, in the complex CONH36, 3 positive and COF6 3 negative. The oxidation state of cobalt is +3, but the former is low spin complex and the later is high spin complex. Fourth, it does not predict the relative stabilities of different complexes. We know that certain complexes are labile, in which the displacement of ligand takes place rapidly, while some are inert, in which ligand displacement by another ligand is very slow. Valence bond theory does not explain the kinetic inertness of complexes such as Cr3 and low spin CO3 octahedral complexes. Fifth, it does not explain the variation of magnetic moment values with temperature. Sixth, it does not take into account the splitting of d energy levels. Seventh, it does not predict the relative stabilities of different structures. Eighth, the valence bond theory does not predict whether the 4-coordinate complex will be square planar or tetrahedral. This can be explained only on the basis of magnetic moment values of the complex. For example, the decision about the geometry of Ni2 complex depends upon the magnetic moment values. For example, Ni2 ion has the electronic configuration 3d8. If the complex involves sp3 hybridization, it would have tetrahedral structure. For the information of tetrahedral structure, the 3d orbitals remain unaffected and the complex is paramagnetic. On the other hand, if the complex involves dsp2 hybridization, it would have square planar structure. This is possible if the two unpaired d electrons are paired up, thereby making one of the 3d orbital empty. This is thus no unpaired electron and the complex would be diamagnetic. It also fails to give a satisfactory explanation for the formation of square planar tetraamine, copper 2 ion, CuNH3 4 2 positive. Ninth, the valence bond theory does not tell us why water and halide ions commonly form the high spin complexes while cyanide ions form low spin complexes. To answer some of the above problems, let us discuss other theories. Crystal field theory, CFT. The crystal field theory was developed by H. Beth and V. Black. This theory is based on entirely different assumption than the valence bond theory. As we have already learned, the valence bond theory considers the bonding between the metal ion and the ligands as purely covalent. On the other hand, the crystal field theory considers the bond between metal ion and the ligand as purely electrostatic. This theory is based on the assumption that the metal ion and the ligands act as point charges and the interaction between them are purely electrostatic. In case of negative ligands, the interactions with metal ions are ion-ion interactions. If the ligands are neutral molecules, the interactions with the metal ion are ion dipole interaction. For example, in the case of complex ion COF6 3 negative, the interaction are between CO3 positive and F negative ion, whereas in CONH3 6 3 positive, the interaction are between negatively charged end of NH3 molecule and CO3 positive ion. The central idea of this theory is that the electrons of the metal ion in the environment of other ions or molecules, as for example within the lattice of a crystal, are affected by the non-spherical electric field established by the surrounding ions or molecules. The electric field was called by crystalline field, but now it is called as crystal field. This is responsible for the name crystal field theory. Basis of crystal field theory. The basic assumptions of crystal field theory are: first, the transition metal ion is surrounded by the ligands with lone paired electrons. Second, all types of ligands are regarded as point charges. The ligands may be either ionic or molecule. If the ligand is a neutral molecule, then the negative end of the dipole is oriented towards the metal ion. For example, ammonia NH3 is polar molecule having del negative charge on N and del positive charge on H atoms. Similarly, water is also polar with del negative charge on O and del positive charge on H atoms. Third, the interaction between the metal ion and the negative ends of an ion is purely electrostatic. That is, the bond between the metal and ligand is considered 100% ionic. Fourth, the ligands surrounding the metal ion produce electrical field, and this electrical field influences the energies of the orbitals of central metal ion, particularly d orbitals. Fifth, in the case of free metal ion, all the 5 d orbitals have the same energy. These orbitals having the same energy are called degenerate orbitals. This means that an electron can occupy any one of these 5 d orbitals with equal ease However, on the approach of the ligands, the orbital electrons will be repelled by the lone pairs of the ligands. The repulsion will raise the energy of the d orbitals. If all the ligands approaching the central metal ion are at equal distance from each of the d orbitals, the energy of each orbital will increase by same amount. Therefore, these orbitals will still remain degenerate, but they will have higher energy than before. But we know that d orbitals have different orientations, and therefore these orbitals will experience different interaction from the ligands. The orbitals lying in the direction of the ligands will experience greater repulsion, and their energies will be raised to greater extent. On the other hand, the orbitals lying away from the approach of the ligands will have lesser interaction, and therefore their energies will be raised to lesser extent. Therefore, due to electrical field of the ligands, the energies of the 5d orbitals will split up. The conversion of 5 degenerate d orbitals of the metal ion into different sets of orbitals having different energies in the presence of electrical field of ligand is called crystal field splitting. This concept forms the basis of crystal field theory. Sixth, the number of ligands and their arrangement around the central metal ion will have different effect on the relative energy of the 5d orbitals. In other words, the crystal field splitting will be different in different structures with different coordination numbers. Seventh, the magnetic properties, spectra, and preference for particular geometry can be explained in terms of splitting of d orbitals in different crystal fields. Thus, to understand the crystal field theory, it is essential to have a clear picture of the position of the 5d orbitals in space and the geometrical arrangement of the ligands around the central metal ion. We may illustrate that this concept by considering the complexes with coordination number 6 and 4, which are very common. Shapes of d orbitals. There are 5d orbitals. These are designated as dxy, dyz, dzx, dx square minus y square, and dz square. The shapes of these orbitals are described below. First, the three orbitals dxy, dyz, and dzx are similar and each consist of four lobes of high electron density lying in xy, yz, and zx planes respectively. These lobes lie in between the principal axes. For example, in case of dxy orbital, the four lobes lie in xy plane in between the x and y axes. Second, the dx square minus y square orbital has also four lobes of high electron density along the principal axis x and y. It may be noted that this orbital is exactly like dxy orbital except that it is rotated along through 45 degree around the z-axis. Third, the dz square orbital consists of two lobes along the z-axis with a ring of high electron density in the xy plane. It may be noted that although dz square and dx square minus y square orbitals do not look to be similar, yet they are equivalent so far as interaction with the metal ions are concerned. The dz square orbital can be regarded as a linear combination of two orbitals, dz square minus x square and dz square minus y square, each of which is equivalent to the dx square minus y square orbital as shown below. However, it may be noted that these two orbitals do not have independent existence, but the dz square orbital can be thought of as having the average properties of the two. Since both orbitals dz square minus x square and dz square minus y square have high electron density along the z-axis, therefore dz square orbital has high or large fraction of electron density concentrated along z-axis. Moreover, one of component orbital has lobes along the x-axis also, and the other hand has lobes along the y-axis. The resultant d orbital has electron density in xy plane shown as Dupnut ring or a collar. Crystal field splitting in octahedral complexes. In an octahedral complexes, coordination number 6, the metal ion is at the center of the octahedron and the ligands are at the 6 corners as shown in figure 3. The three axes x, y, and z point along the corners of the octahedron and are also shown. Let us suppose that the metal ion Mn positive has a single d electron. In the free ion, when there are no ligands, the electron can occupy any one of the 5d orbitals because all are of the same energy and are called degenerate orbitals. However, in octahedral complex mx6, all the 5 d orbitals will not remain of equal energy. This can be easily understood by considering the shapes of these orbitals in the octahedral field of the ligand. The comparison of arrangement of d orbitals in figure 4 shows that the two lobes of dz square orbitals and four lobes of dx square minus y square orbital point directly towards the corners of the octahedron where the negative charge of the ligand are concentrated. The remaining three orbitals are oriented in between the axes. In the case of octahedral complex, the former two orbitals are designated as Eg orbitals while the lattice three orbitals are designated as T2G. As the two ligands approaches the central ion along the axis, the Eg orbitals are repelled more than the two T2G orbitals. In other words, the energy of the dz square and dx square minus y square orbitals increases much more than energy of the dxy, dyz and dzx orbital. It should be remembered that when a charge is repelled by a similar charge, its potential energy increases. The greater the repulsion, the greater is the increase in energy. Thus, in octahedral complexes, the 5d orbitals split up into two sets. One set consisting of two orbitals of higher energy and the other set consisting of three orbitals of lower energy. The phenomena of crystal field splitting in an octahedral complex is illustrated in figure 5. The energy difference between two sets of d orbitals T2G and Eg is called crystal field splitting energy and is symbolically represented as del naught, stands for octahedral. The magnitude of del naught varies for different complexes. The crystal field splitting is also measured in terms of another parameter called dq. The two are related as del naught is equals to 10 dq. These two parameters are very commonly used. It may be noted that the crystal field splitting occurs in such a way that the average energy of the d orbitals does not change. This is known as barycenter rule, which is similar to center of gravity type rule. This means the decrease in energy of the set of orbitals that lie at the lower energy level must be balanced by the corresponding increase in other set. Therefore, in terms of total energy 10 dq, the energy is each of the two Eg orbitals is raised by 6 dq and the energy of each of the three T2G orbitals is lowered by 4 dq. In terms of del naught, the energy of each of the two Eg orbitals is raised by 3 by 5 del naught or 0.6 del naught and the energy of each of the three T2G orbitals is lowered by 2 upon 5 del naught or 0.4 del naught. The value of 10 dq or del naught is measured spectroscopically. In figure 5, we observe that initially the energies of all the 5d orbitals are raised equally as shown in state second. This would be observed if the field created by the ligands were spherically symmetrical. However, the energies of d orbitals split into two sets because of the different orientation of the orbitals towards the ligands as shown in state 3. Crystal field stabilization energy. We have learned that in an octahedral field, the energies of 5d orbitals split up. 3 orbitals are lowered in energy and 2 orbitals are raised in energy. We know that electrons always prefer to occupy an orbital of lower energy. For example, in the case of d1 system, the d electron will prefer to occupy a T2G orbital and is therefore stabilized by an amount equal to 0.4 del naught or 4 dq. The amount of stabilization provided by splitting of the d orbitals into two levels is called crystal field stabilization energy. It is abbreviated as CFSC. Thus, in octahedral field, for each electron entering into the T2G orbital, the crystal field stabilization is minus 4 dq. For each electron entering into the Eg orbital, the crystal field destabilization energy is plus 6 dq. Thus, the CFSC is calculated as the algebraic sum of minus 4 dq per electron in T2G level and plus 6 dq for each electron in Eg orbital. CFSC for various octahedral complexes. First, for a d1 system, electron will be present in any one of three T2G orbitals. The electronic configuration may be written as T2G1. The crystal field stabilization energy is minus 4 dq. Second, for a d2 system, the electron will occupy T2 orbital with their spins parallel in accordance with Hund's rule. The electronic configuration is T2G2 and crystal field stabilization energy is minus 8 dq. Third, similarly for a d3 system, the electronic configuration is T2G3. The crystal field stabilization energy is minus 12 dq. Fourth, for a d4 system, there are two possibilities. A. All the 4 electrons may occupy T2g orbital with 1 electron gets paired. The electronic configuration may be written as T2g4. Second, 3 electrons occupy T2g orbital and the 4th electron goes to one of the Eg orbital. The configuration may be written as T2g3 Eg1. The actual configuration may be decided on the basis of del naught and the pairing energy P, that is the energy required to pair the electrons with one another. The configuration is possible if del naught is greater than P. These complexes are called strong field complexes because del naught is large. In the case of complex has less number of unpaired electrons and is called low spin complex. The configuration is possible if del naught is less than P. It is called weak field and the complex are called weak field complexes. In the case of maximum number of electrons remain unpaired and the complex is called high spin complex. Thus, we may generalize that if del naught is greater than P, strong filled, low spin complex. If del naught is less than P, weak filled, high spin complex. As shown above, for a low spin complex having T2G4 configuration, CFSE is equals to minus 16 dq. However, if we take into account pairing energy, also the net CFSE becomes net CFSE is equals to minus 16 dq plus P. On the other hand, for a high spin complex having the configuration T2G3 Eg1, CFSE becomes minus 6 dq. Fifth, for a D5 system, there are two possibilities. A. All the 5 electrons may occupy T2G orbitals with 2 orbitals get paired. The electronic configuration may be written as T2G. This is possible if del naught is greater than P and the complex will be called strong filled or low spin complex. B. The 3 electrons occupy T2G orbitals and 2 electrons occupy Eg orbitals. The electronic configuration may be written as T2G3 Eg2. This will be possible if del naught is less than P and the complex is called weak filled or high spin complex. The CFSE in these two types of complex will be A. Strong filled del naught greater than P, CFSE is equals to minus 20 dq plus 2P. B. Weak filled del naught is less than P, CFSE is equals to 0. Similarly, D6 and D7 systems have two possibilities depending upon the relative magnitude of crystal field splitting energy and the pairing energy of the electron. For a D6 system, A. Strong field del naught greater than P, CFSE is equals to minus 24 dq plus 2P. B. Weak field del naught is less than P, CFSE is equals to minus 4 dq. For D7 system, a strong field del naught greater than P, CFSE is equals to minus 18 dq plus P. B. Weak field del naught less than P, CFSE is equals to minus 8 dq. The D8, D9 and D10 system have only one possible configuration. This is because if we assume the complex to be high spin, the first 5 electrons would be gone each into the 5 d orbitals and remaining 3, 4 or 5 electrons would fill the T2G and Eg orbitals, but if we assume the complex to be low spin, the first 6 electrons would fill the T2G orbital and the remaining 2, 3 or 4 electrons would go into the T2G orbitals. In both cases, the configuration will be the same. Therefore, there is only one possible electronic configuration for D8, D9 and D10 system. For D8 system, CFSE is minus 12 dq. For D9 system, CFSE is minus 6 dq and for D10 system, CFSE is 0. The d electron configuration for weak field and strong field of octahedral symmetry are given in figure 6. The crystal field stabilization energy CFSE for metal ions having different configuration are assumed up in table 2. It may be noted that the strong field, the electrons always pair up in the lower level first, filling it before entering the higher level. For weak field, each orbital, whether of high or low energy, received 1 electron each before any pairing starts. Therefore, weak field configuration always have the same pairing scheme as the free ions. Crystal field splitting in tetrahedral complexes. The coordination number for tetrahedral complexes is 4. The tetrahedral arrangement of 4 ligands surrounding a metal ion may be visualized by placing ligands on the 4 of the 8 corners. Ligands surrounding a metal ion may be visualized of the direction x, y and z point to the center of the faces of the cube. From figure 7, it is clear that the orbitals dxy, dyz and dzx point between x, y and z axis, that is towards the center of the edges. Whereas the orbitals dx square minus y square and dz square point along x, y and z axes, it is clear that in tetrahedral field none of the d orbitals point exactly towards the ligands, and therefore the splitting of energy will be less than that in octahedral field. The 3d orbitals dxy, dyz and dzx are pointing close to the direction in which the ligands are approaching, while the two orbitals dx square minus y square and dz square are lying in between the ligands. Therefore, the energies of the three orbitals will be raised while the energies of the two orbitals will be lowered. Thus, in the presence of tetrahedral field, the degeneration of 5d orbitals split up as: first, the two orbitals dx square minus dy square and dz square become stable and their energies are lowered. They are designated as E orbitals. Second, three orbitals dxy, dyz and dzx become unstable and their energies are raised. These are designated as T2 levels. It may be noted the splitting of d orbitals in tetrahedral field, the subscript g is not used. For example, the orbitals dx square minus y square and dz square are designated as E orbitals, whereas the other three orbitals dxy, dyz and dzx are designated as T2. This is because a tetrahedral geometry has no center of symmetry. Symbol g and u have meaning only for fields which have center of symmetry. This is diagrammatically shown in figure 8. The magnitude of crystal field splitting is the difference between E and T2 orbitals and is designated as del T, indicating tetrahedral complexes. It is also measured in terms of dq, and del T is equals to 10 dq. If we compare the magnitude of crystal field splitting in octahedral and tetrahedral complexes, it has been observed that the crystal field splitting in tetrahedral complexes is considerably less than the octahedral complexes. It has been found to be del T is equals to 4 upon 9 del naught. Reason for the smaller value of crystal field splitting in tetrahedral than in octahedral complexes. There are two main reasons for this. First, in tetrahedral complexes, there are 4 ligands while there are 6 ligands in octahedral complexes. Therefore, lesser ligand produce less crystal field splitting. The crystal field splitting in tetrahedral field is about 2/3 of the octahedral field. Second, in tetrahedral field, none of the orbitals is pointing directly towards the ligand and therefore splitting is less. Since the magnitude of crystal field splitting in tetrahedral field is quite small and is always less than the pairing energy, therefore the pairing of electron will never be energetically favorable. Thus, all the tetrahedral complexes are high spin complexes. No tetrahedral complex with low spin has been found to exist. CFSE for tetrahedral complexes. As we know that an electron always prefers to occupy an orbital of lower energy, since average energy of the d orbitals does not change. Therefore, in terms of 10 dq, the energy of each of the e orbital is lowered by 6 dq and the energy of each of the t2 orbital is raised by 4 dq. CFSE is therefore calculated as the algebraic sum of minus 6 dq per electron in e orbital and plus 4 dq for each electron in d2 orbital. In terms of del T, the energy of each e orbital is lowered by 3 by 5 del T, while each of the t2 orbital is raised by 2 by 5 del T. For example, for d1 system, the electronic configuration is E1, therefore CFSE is minus 6 dq. For d2 system, the electronic configuration is E2, therefore CFSE is minus 12 dq. For D3 system, the electronic configuration is E square T21. As already discussed, crystal field splitting in tetrahedral field is quite small and is always less than the pairing energy. Therefore, pairing does not occur and the most of complexes are high spin complexes. Therefore, CFSE is minus 8 dq. The CFSE of complexes with metal ions having different configuration of d orbital in tetrahedral field are given in table 3. For D1 minus 6 dq, for D2 minus 12 dq, for D3 minus 8 dq, for D4 minus 4 dq, for D5 0, for D6 minus 6 dq, for D7 minus 12 dq, for D8 minus 8 dq, for D9 minus 4 dq and for D10 0. Crystal field splitting in tetrahedral, tetragonal and square planar complexes. The splitting of d orbitals in tetragonal and square planar complexes can be easily understood from the non-splitting of d orbitals in octahedral complexes. This is because tetragonal and square planar geometries can be understood by withdrawing two trans ligands from an octahedral complex. This process is called elongation. Generally, we consider the removal of trans ligands along the z-axis. As the ligands lying on the z-axis are moved away, the ligands in the xy plane tend to approach the central ion more closely. As a result of increase in metal-ligand bond along z-axis, the repulsion from the ligand to electron in dz square orbital decreases, and therefore the energy of dz square orbital is decreased relative to that in octahedral field. At the same time, the metal ligand bond along x and y are shortened so that the d orbital in xy plane dx square minus y square experiences greater repulsion from the ligands, and therefore its energy is raised. Similarly, the dxz and yz orbitals are lowered in energy because decrease in repulsion effect along the z-axis, while the energy of dxy orbital is raised. The resulting splitting pattern is shown in figure 10. This state represents tetragonally distorted octahedral structure. As the transligands lying along z-axis are completely removed, a square planar complex is formed. In the square planar complex, there is further rise in the energies of dx square minus y square and dxy orbitals, and a further fall in energies of dz square, dxz and dyz orbital as shown in figure 10. It has been observed that in square planar complex, the energy of dz square orbital falls even below the dxy orbital. The change of octahedral complex to tetragonally distorted octahedron and finally to square planar arrangement is shown in figure 11. It may be remembered that tetragonally distorted structure can be obtained when the two transligands are brought closer to the metal ion. This is called flattening of an octahedron. This is shown in figure 12, where figure 12a shows elongation of octahedron. In flattening of octahedron, the two trans Ml bond are shortened while other 4 Ml bond become large. The splitting of energies of d orbitals will be reverse of what has been observed in the case of elongation. Crystal field splitting in trigonal bipyramidal complexes. The coordination number for trigonal bipyramidal complexes is 5. In trigonal bipyramidal geometry, the three ligands lie along the corners of an equilateral triangle at an angle of 120 degrees, each forming the pyramid base in xy plane. The two ligands lie perpendicular to the base triangle along z-axis as shown in figure 13. It is clear from figure 13 that the dz square orbital points exactly towards the ligands, and therefore it will be most unstable and hence its energy will be raised to the maximum extent. The two d orbitals, that is dx square minus y square and dxy, lie in xy plane. The lobes of these two orbitals point exactly towards the ligands but close to the direction in which the ligands are approaching, and hence will be stable in comparison to dz square orbital, and their energies will be lowered. Similarly, on the other two orbitals, that is dyz and dzx, lie quite away from the approach of the ligand and hence will be lowered to greater extent than even dx square minus y square and dxy orbitals. The splitting of 5d orbitals in trigonal bipyramidal field of ligands is shown in figure 14. Then there are few examples to calculate CFSE values. Factors determining the magnitude of crystal field splitting. The following factors influence the magnitude of crystal field splitting. First, nature of ligand, spectrochemical series. The crystal field theory depends upon the nature of the ligand. The greater the ease with which the ligand can approach the metal ion, the greater will be the crystal field splitting caused by it. The ligands which cause only a small degree of crystal field splitting are called weak field ligand, and which cause large splitting are called strong field ligands. The spectrochemical series in an experimentally determined series, it is very difficult to explain the order because it incorporates the effect of both sigma and pi bonding. In general, the variation and the splitting is caused by a number of factors such as small ligands can cause greater crystal field splitting because they can approach the metal ion closely. For example, F negative ion produces more del naught value than large chlorine negative and Br negative ions. B. The ligands containing easily polarizable electron pair will be drawn more closely to the metal ion. C. The ligands which have greater tendency to form multiple bonds such as Cn negative and NO2 negative cause greater crystal field splitting. The very high crystal field splitting produced by Cn negative ligand, about double that for weak filled ligands like halide ions. These is attributed to the pi bonding in metal. The metal donates electrons from a filled T2g orbital into the vacant orbital on the ligand. D. The following pattern of increasing sigma donation is observed. C donors the highest, then N donors, then O donors, and halide donors the least. The effect of crystal field splitting del naught on the ligands attached to Cr3 is shown below. The common ligands can be arranged in any increasing order of crystal field splitting del. The regular order is called spectrochemical series. The order remains almost same for the different metal ions. The spectrochemical series in the increasing order of crystal field splitting is given by weak field ligands I negative, Br negative, SCN negative, Cl negative, NO3 negative, F negative, OH negative, OX square negative, H2O, EDTA, PYNH3, EN, DIPY, O phenyl, NO2 negative, CN negative, and CO. From the series, it is clear that CO, Cn negative, and NO2 negative are strong field ligands, whereas I negative, Br negative, and SCN are weak field ligands. In general, the ligands up to NH3 are called weak field ligands, while those on the right of NH3 are called strong field ligand. The order of the spectrochemical series remains practically same irrespective of the transition metal ions. Second, oxidation state of the metal ion. The magnitude of the crystal field splitting depends upon the oxidation state of the transition metal ion. The metal ion with higher oxidation state causes larger crystal field splitting than in done by the ion with lower oxidation state. For example, the crystal field splitting energy del naught for COH2O6 3 positive complex, in which the oxidation state of cobalt is plus 3, is 18,600 per centimeter, whereas for the complex COH2O6 2 positive, in which the oxidation state of CO is plus 2, del naught 9,300 per centimeter. Similarly, for the complex FeH2O6 3 positive and FeH2O6 2 positive, in which iron has oxidation state plus 3 and plus 2 respectively, the values of del naught are 13,700 per centimeter and 10,400 per centimeter respectively. This is clear from the following data, in which crystal field splitting energies for hexa aqua complexes of M2 positive and M3 positive ions of the first transition series are given. Similarly, for complexes having other ligands, the del naught values in lower oxidation state are smaller than del naught values in higher oxidation states. Extent of crystal field splitting for similar complexes of a metal in the same oxidation state increases by about 30 to 50% on going from 3D series to 4D series. The increase is almost of the same amount on going from 4D series to 5D series. This may be explained on the basis that 4D orbitals in comparison to 3D orbitals are bigger in size and extend farther into space. As a result, the 4D orbitals can interact more strongly with the ligands, and therefore the crystal field splitting is more. Similarly, 5D orbitals are bigger than 4D orbitals, and del naught for the third transition series is more than that of second transition series. This is evident from the following data. Fourth, geometry of the complex. As mentioned earlier, the crystal field splitting energy of tetrahedral complex is nearly half the value for octahedral complex. In other words, the value of splitting energy for tetrahedral complexes in general is small as compared to the pairing energy P. The tetrahedral complexes are therefore mostly high spin complexes. Then there are few examples regarding configuration. Thank you.